Alright, section 1.4 is on page 35, talks about functions. Functions is a special relation between two variables, x and y, for the most part. It could be any other variables, but we use x and y because that's what we're going to use most of the time. So, a relation, this is the definition, our definition, a function is a relation of distinct pairs in which the first coordinate, which is the x value, does not repeat. So, anytime you're given a relation, you look at the x values. If the x values don't repeat, automatically it's a function. And if they do repeat, it's not a function. Associated with any relation, specifically functions, but relations in general, is domain and range. Domain is what's allowed for x, range is what's allowed for y. And we call domain the input and range the output. Not that big of a deal for us, but we need to know that whatever you could allow x to be, that's domain. Whatever you allow y to be, that's the range. And we'll talk about that a bit more through the examples we're going to do. Here's example 1. Determine if the following relation represents a function. State the domain and range of each relation. And I have 4 given points. So if I glance at these points, one way of doing that is to say, well, look, does the x repeat? Here's x. X equal 1 in the first pair, x equal 2 in the second pair, x equal 4 in the third pair, and x equal 5 in the last pair. Since x does not repeat, you say, guess what? This is a function. That works. Very good. Then they say, state the domain and range. Well, it's really simple. Domain is allowable x values. What x values are there? 1, 2, 4, and 5. And range is simply allowable y values. So, 2, 3, 6. No need to list 6 twice. There it is. 3 values in the range. Done. And here's another example. Again, I look at this, say, okay, well, is this a function? Example B. I notice, okay, that's 1, 2, 4, and 1. I go, wait a minute. 1, 2. That's not the same point. Those are different points. Well, because x appears twice, we say that's not a function. Now, normally domain and range is associated with functions, but D for domain, range for R for range. Still, I could list the domain as 1, 2, and 4, and the range as, what do we have? Range would be the allowable y values. What are the y values? That is a 2, 3, 6. Now, I want to show something really quick. If I was to plot the points on the first problem, and if I was to plot the points on the second problem, they're not asking for that, but if I was to look at example A and plot the points, and example B and plot the points, I would notice that on the first one, 1, 1, 2, that's a point, 2, 1, 2, 3, 3, 4, 1, 2, 3, 4, 5, 6, and 5, 3, 4, 5, 6. There. That's what a function looked like. And if I was to look at the domain, it's these x's. Oops, not that one. That x and that x. And if I was to talk about the range, that would be those 3 y's right there. If I was to plot the second piece, this 1, 1, 2, 2, 1, 2, 3, very good, 3, 4, 1, 2, 3, 4, 5, 6, and 1, 1, 2, 3, 4, 5, 6. So here I notice I have 2 values that are the same y. You could tell right there. But that didn't matter. Here I notice I have the domain being x appears twice right there. And the range is really those values. Again, whether the y repeat or not is irrelevant. By x repeating twice, do you notice that if I was to fit this, that would fit on one line? And why am I talking about a vertical line? Because x equal 1 is a vertical line. Do you see that it touches twice? And from here, well, you are asked to figure out whether a relation represents a function in 3 different types of problems. Points I just did. There are none in the book, so I added problems to you. A graph. Well, graphically, if I'm given a graph, if I'm given a graph, let me check. Alright, so here's the vertical line test, and they get that out of the original definition because, as we mentioned, if you line up the points with a vertical line and it crosses more than once, that means x repeats more than once and therefore not a function. So, a relation represents a function if no vertical line intersects its graph more than once. So, you look at the graph, and 7, and I'm altering 2, I'm making that 2 prime. They're asking us to figure out if this is a function or not. The way we do this, we graph it. Absolute value, a basic graph, shift it to the left 2 units. So the graph looks something like this. And they're asking, is this a function? Well, if I draw a vertical line, and this is basically what you're thinking. You're thinking, can I draw you think backwards, you know? Can I draw a vertical line anywhere on this graph in which I'll get more than intersection? If the answer is no, you would say, you know what? Yes, this is a function. And if you look at number 2, that's a circle centered at the origin with a radius of 2. And if you sketch a graph, it looks like this. And what do you notice? Once you put a line, well, you only need one exception. Since that intersects more than once, we say this is not a function. And that's how it works. Oh, I don't like that word. Let me write it better. There we go. Now, on number 10 and on, they give us the graph. From number 10 and on, they give us the graph. Oh, what happened? Oh, 2 different, okay, I get it. Move this right here. There we go. Right, it's separated from this. Okay. On number 10, they give you the equation. Don't let the equation throw you out because they provide the graph. And here they say, well, okay, is this a function? Well, you draw a line, and what do you notice? That crosses once, another line. Well, can you find anywhere on this graph where you draw a vertical line that crosses more than once? If that's not the case, you would say this is a function. Now, on the next set of problems, they boost it up. They say, hey, find the domain and range. They're not asking if it's a function. You could check, but they're saying, find the domain and range. Now, graphically, we said allowable x values. So you're taking this path left to right, and you're looking at the x, figuring out how far to the right is this graph going to go. Do you agree that this graph starts at 1.5 included and trends all the way to infinity? That's the domain. The range allowable y values, you're taking this path, but instead you're looking at how high is it going. Well, doesn't that start at 0 and go all the way up? Now, a quick refresher. When we talk about domain and, oh, that's why I had this here. Whenever we talk about domain and range, domain is allowable x values. We said that already. Generally speaking, when you ask for the domain, domain is all real numbers unless we see one of 3 functions. Unless we see fraction. And in the fraction, we want the denominator not to equal 0. An even index radical. And with an even index radical, we want the radicand, the quantity underneath the radical, to be bigger than or equal to 0, provided n is even. And a log, we're not going to talk about a log yet because that's the next section. When we get there, we'll talk about it in full details. A log behaves, you know what, might as well since we're here. A log, base A of a log of A, and with a log, oh, I love it when this gets stuck like that. There we go. Let's fix that. Again, n has to be even. Cube roots don't have a restriction. If you're talking about the log, then here you want A to be strictly bigger than 0. So those two look very much alike. Well, on number 24, we're not going to graph this because that's a lot of work. Instead, we say, look, I see a fraction, take the denominator, and figure out where would the denominator equal 0. That's when x equal 1. X equal 1 is the only value that makes the denominator equal 0. So domain is any x value such that, what's the condition? Stay away from 1 and you're okay. And if I look at this example, I have two things going on. Domain, to talk about domain, one, I see a fraction, and I see a radical, and the index is even, right? I see a fraction. So first things first, I take the fraction and say the denominator cannot equal 0. Where does it equal 0? So basically, I'm saying stay away from 3. The radical says take what's underneath that radical and solve that inequality. So how could you find a region that satisfies both of those? One of them say, hey, stay away from 3 and everything's okay. The second one says 3 or above. Well, wouldn't you say the domain to satisfy this case and this case simply take 3 out of the equation and run to infinity? So an even index radical, you would set what's inside of it to be bigger than or equal to 0 unless it is in the denominator. You would simply set whatever is inside to be strictly bigger than 0 and solve it. That will work as well. So if I were to take the equal out, that will take care of the fraction as well. Alright, now the next level up, we want to evaluate functions. So anytime you're given a function, you take y and you replace it by f of x. F of x. That's Euler's notation. A famous guy. Very famous. Well, let's see. So basically what this says y equal x squared minus 4x plus 1. What is the same? Well, notice they replaced the x by a negative 1. Well, replace the x by a negative 1. If I replace this x and that x by a negative 1, so it's kind of like you doing this. If x equal negative 1, find y. That's exactly what it is. Wouldn't that be 1 plus 4 plus 1? wouldn't that be 4, 5, 6? So basically what this is saying, when x equal negative 1, y equals 6. That's the answer right there, but that's what it means. And if I would go ahead and figure out what this is, again, this is saying if x equal 1/2, what does y equal? Well, we know that y equal 1/2 squared minus 4 times 1/2 plus 1. That is 1/4. Half of 4 is 2. That is 1/4 minus 1. The common denominator is a 4. 1 minus 3 is negative negative 2/4, which is negative 1/2. So, not that bad, just some evaluation. You've seen this before, I'm just reminding you of it, and if you remember it, here it is. C is really the key. This is a bit off. They're replacing this x by c minus plus 2. So it's going to be c plus 2 squared, just like you did right there, minus 4 times c plus 2 plus 1. I gotta work on my 2's. They look horrible. So again, just like here, you replaced x with negative 1. Here, x with 1/2. Here, you replace x by that mess, and you proceed the same way. To clean this up, if you FOIL, that's c squared plus 4c plus 4 minus 4c minus 4c plus minus 8. 4 times 2 is 8 plus 1. So that is c squared. Those cancel out. That doesn't happen all the time. 4 minus 8 is negative 4 plus 1 is negative 3. Almost done. 2 more things we need to find. Something that's coming up heavy for us, difference quotient. Find what this is. Well, to do this, this has 3 components, right? So to find that, I would really go ahead and work out each part individually. That is, I'll figure out what this is. I'll say what's h of z plus x plus delta x. In this case, you're going to replace x plus delta x squared plus x plus delta x plus 3. You're going to clean that up. X squared plus twice x delta x plus delta x squared. This you just copy down. And if you combine like terms, oh, actually that's all there is. Nothing is common. Nothing combines. So that's it right there. Nice. Now I know that this right here is this right here. So if I would go ahead and say, well, that is, if I replace it, x squared plus 2x times delta x plus delta x squared plus x plus delta x plus 3 minus h of x. Do you see h of x is just y? It's this. All over delta x. Well, if I distribute this negative n, doesn't that become negative x squared minus x minus 3? And do you notice then, this will cancel with this will cancel with this, and this will cancel with this. I'm left with 2x delta x plus delta x squared plus delta x over delta x. And do you notice they all have a delta x? If I factor that out, I'll have 2x plus delta x plus 1. And once I cancel the denominator, I'm done. Every time you see the statement, difference quotient, your goal is to cancel that denominator. Same thing with number 34. your goal is to cancel that denominator. Once this is cancelled, you're done, but it's going to take some time. Let's see. Let me start with this piece. What would f of x plus delta x equal? F of x plus delta x is 1 over x plus delta x plus 4. Again, the only place that's going to change is that 4. Hey, that's this piece. So now if I substitute that in, that is 1 over x plus delta x plus 4 minus f of x. Well, f of x is literally right there. All over delta x. So this is a complex fraction. I could do this two ways. I am going to cover this in a full section, but I'm waiting until probably next week. Well, I'm going to do this sort of the long way. That is, I'm going to say, what is the common denominator for the top? Wouldn't that be x plus delta x plus 4 times x plus 4? And what is this missing to have the whole LCD? And x plus 4. And what is this missing? You have to multiply by x plus delta x plus 4, x plus delta x plus 4. So this is minus 1 times x plus delta x plus 4. And if I say this is x plus 4 minus x minus delta x minus 4 over the LCD, that would be those two cancel out and those two cancel out. That's really negative delta x over x plus delta x plus 4 times x plus 4 divided by delta x. And instead of dividing, can't you multiply by the reciprocal? We're doing this the very long way because there's only one problem. We are going to really get mixed fractions out of the way. So when you multiply by the reciprocal, once that cancel out, you're done. Negative 1 over x plus delta x plus 4 into x plus 4. Again, I'm going to cover a section on complex fractions coming up. One more thing to do, and we're done. If f of x is 1 over x, and g of x is x squared minus 1, if I work this using order of operations, isn't this saying find the value when x equal 2? But which 2 are they talking about? They're talking about 2 associated with this y. If x equal 2, what do you get? Don't you get a 2 squared minus 1? Isn't that 4 minus 1, which is 3? And now what is this saying? So this is like a puzzle. It's saying, hey, if x equal 3, what does y equal? Which y? This y. So wouldn't that be 1 over, just throw the 3 in, and that's what y equal? 1/3. Let's do it again. But right there, with b. If you look at b, b is saying g of f of 2. Well, let's see. This is saying if x equal to, what does y equal? So you're always looking for a y value. But which y value? I have this y and this y. Obviously, f associated with this. Well, if f of x, so if y equal 1 over x and x equal 2, if you put a 2 there, isn't that 1/2? I just figured out what this is. So if I put 1/2, and again, order of operations from the inside of the parentheses out, what is it saying? What does y equal when x equal 1/2? But we just did it. We just did it for this function. This is saying now go to this function. Isn't y equal x squared minus 1? Put a 1/2 there. Isn't that 1/2 squared minus 1? 1/4 minus 1. That's negative 3/4. That would be the answer. And what if they didn't give us an x? Oh boy. They're saying, what does y equal? Well, what do you think y equals? Let's go color code those. What does y equal? Y equal all of this, x squared minus 1. Do you know what this is saying now? Take this and put it right there. Wouldn't that be 1 over x squared minus 1? And what if I go the other way around? What if I went from the inside of the parentheses out? Now I'm looking at, what does f of x equal? Well, that is y equal 1 over x. And do you know what this is saying now? This is saying, go to the g, there's g. What's up, g? And replace x, that x, by 1 over x. Wouldn't that be 1 over x squared, and you would subtract the 1? Wouldn't that be 1 over x squared minus 1? And if I get a common denominator, that will be 1 minus x squared over x. And there's your homework.